morning. This is Andy Schweitzer, and I'm going to run through three different enthalpy or delta H calculations that you will likely to see. They're involving just some stoichiometry, which we've already covered in a previous video, bond energies, and Hess's law. So this will be just one example of each in the general concept that's we're dealing with. So this is a thermodynamic equation. Now, when I call it a thermodynamic equation, I'm referring to the fact that I've already calculated out how much energy is going to be involved here. When I have this reaction, it means that 2 moles of this guy plus 9 moles of the oxygen yield 6 moles of carbon dioxide, and 8 moles of the water will and also give off some heat. This amount of energy is that much. So every time you cycle through one time, we get this much energy. So there's a relationship that says 2 moles of C3H8O will give me, if this much energy, 4,011 kilojoules of energy, and that's going to be released. That's the fact that it's negative. I could rewrite this and have it, okay, for 1 mole of this, 4.5 moles of this, 3 moles of this guy, 4 moles of this guy will give me, in this case, delta H for this reaction would be 2,000, we'll cut 11.5 would be, and 5.5, I'm not doing exactly in half because I didn't look at that 3 there, all right, but that would be my new delta H. So if I cut all my coefficients in half, I also need to cut this in half. I'm using half as much of materials, I get half as much energy. It's all just proportional. And sometimes you'll see these halves in here and just go with it as it is. This number of moles gives me this much energy. Same as if I go 2 moles gives me this much energy. It's the same proportion. So in this case, the typical problem you'd see is, okay, what if I have 50 grams of C3H8O. I want, if I burn this stuff, how much actual energy will I get out? Okay. Well, this says for every 2 moles of this, I get 4,000 kilojoules of energy, and that's just what I'm using. I could use the 1 to 2005; it'd be the same difference. But this is a mole calculation. So first thing, I'm going to go 50 grams, get rid of grams, and go to moles. Get rid of moles and go to kilojoules of energy. And first things, you add up all the molar masses of these guys. 1 mole of this weighs how much? And at this point, I'm not even going to calculate this out. I'm just simply going to say you put your mass in here. Then easily can calculate moles. And then here, the relationship is 2 moles of this stuff gives me 4,011 kilojoules of energy. If you make it negative, you're just assuming that you're implying that energy is being released. 50 divided by the molar mass times 4,011 divided by 2, it gives me my amount of energy in kilojoules that is going to be released. And that's just one example. We gave those earlier, but that's it for now on those particular examples. Moving on to bond energies. Okay, now with bond energies, this is what I refer to as maybe the simplest explanation of bonding that you could have. Bonds are broken, bonds are formed. Energy is involved. When you break bonds, okay, you should understand when you break bonds, okay, energy is released. And when you form bonds, okay, in that sense, energy needs to be added to form a bond, okay? And that sometimes gets, people get that backwards or whatever, okay? But doesn't, at that point, to do the mathematics, it doesn't really matter. But either way, the equation is that, okay, if I take all my bonds of my reactant bonds, the ones I'm going to break, and break all those, and then subtract that from all the energy required to make all your new bonds, okay, your products. Subtract those energies, and you get your difference in energy, which is going to be your delta H. which is your heat released. So when I look at a reaction, I want to be able to, and again, you need to have a little more in-depth knowledge of some Lewis structures of these things. For our particular class, sometimes we haven't done a lot of this yet in the advanced chemistry, but we will, and you should be able to pencil through it and see what's going on. What I do is at this point, it's balanced for me, 1, 2, 1, 2. So let's draw a pictorial version of this. I have a CH4 molecule plus an O2, and I have 2 of them, will yield a CO2, looks like that, just one of them, and I have 2 water molecules. Okay. Now, if the bonds are the same on both sides, like if you have a whatever, I guess they're all different here, but if you had a certain X bond here and the same bond was over here, technically you could just cross it out on both sides and not worry about it. Or you can just add them up on both sides and they'll eventually subtract out. But on this side I have 4 carbon-hydrogen bonds and I have 2 oxygen double bonds. And each of those are assigned a value, and you have a bond energy chart in the science resources on my website. You can pull it up if you haven't been given one yet. But in this case, the double bond is worth 502 kilojoules per mole, kJs per mole. So on that point, I will times this thing by 2, because I'm going to go with 1 mole of this, 2 moles of this yields 1 mole and 2 moles. So that's going to be a whopping 1,004 kilojoules of energy for this reaction. And this guy is 414, and there's 4 of them. 1, 2, 3, 4, and times 4, and it's too early in the morning. I'll just multiply that. 414 times 4 is 1656. 1656 kilojoules of energy. Over here on this side I have 2 carbon-oxygen bonds. Those are worth 730 a piece, so there's 2 of them, which is going to be 1460 kilojoules of energy for that guy. And then on this guy I have my oxygen-hydrogen bond, and there's 1, 2, 3, 4 of those. The oxygen-hydrogen bond is 464 times 4. 464 times 4 equals 1856. Alright, so we're going to look at the bonds broken minus bonds formed, and it'll be as simple as this. We got 1004 plus the 1656. Now keep in mind, in a lot of these state function calculations, we do the products minus the reactants. It's backwards here. We're doing bonds broken, which is the reactants, minus bonds formed, which is the product. So it's backwards of our normal state function calculations. This guy here is going to be 1004 plus 1656 equals 2660 minus, I have my 1460 plus my 1856 equals 3316, and of course you take your 2660 minus gives you a negative 656 kilojoules of energy, and this is equaling your delta H for this reaction. And again, we'll have this stuff involved in quizzes. Just one example of how it works, and all the rest of them are pretty much the same. Okay. All right, next. So our last little section here is about Hess's law. Now, Hess's law, as we have seen from earlier chapters, that chemical reactions can add up to equal one larger process, which we call these smaller ones elementary reactions. So we could have, so for example, we've had situations where we have reaction, let's go reaction A, capital A, and then we have reaction B, and add those up, give you reaction A, B. Of course, you would take all your reactants from one side, all your reactants, add them together, and give you all of your reactants, and then of course you add all of your products up, give you all your ending products, cancel out like terms, and you have your overall reaction. You know, in kinetics we did this with individual elementary steps, and they were proposed mechanisms. But you should note that any chemical reaction can be added up to equal an overall larger process if everything cancels and it all works out. Well, individual A, it says here, has a delta H that is giving away a negative 10 kilojoules of energy. Then reaction B has a delta H which is taking in 5 kilojoules of energy. So you should note that adding these two up just gives me a net difference, delta H, which is going to be a negative 5 kilojoules of energy. Okay, so in any reaction, the enthalpies of individual reactions will add to equal my overall delta H. That should be fairly apparent. Energy is like money. If one process you lose money, one process you gain money, you just add the two together for your net difference. It is a bit of a state function. Now, in this case, I have an example, and I will walk through this example and give a few different tidbits of information about it very quickly. The goal here, very often, is they give you an overall reaction, and they want you to determine the delta H for this particular reaction. They give you subsequent either proposed reactions or well-established reactions, and they have a delta H available with them. So we want to manipulate these equations so that they add up to the overall. And so it's a bit of a game here. I need to flip and multiply coefficients, adjusting my delta H on the fly, so that when I add these reactions up, they equal the overall. So it's kind of a fun little game. In this case, when I flip a reaction, so maybe my reactants and products are on the right sides, then I flip the sign from a positive to negative. What goes in has to equal what's coming out. The forward is exothermic, the reverse is endothermic. So either way, if I flip things, I need to change my signs. If I need to multiply any coefficients, then at that point, if I multiply my coefficients, okay, let's say I have to multiply everything times 2. Well, then that means I have twice as many particles going through the process, which means my delta H gets multiplied by 2. And this is, if I divide it by 2, then I have half as much stuff going through. The delta H gets divided by 2. So it's proportional. Whenever you do multiply and divide, you must also do to the delta H. And we'll see some examples of that as we move along here. Now, the first thing I do when trying to set up these individual reactions is I try to figure out, are my reactants and products on the right sides? Okay. So as I look at this, my reactant is H2SO4, producing sulfur trioxide and water. And I notice right off the bat that my main reactant is on the wrong side. This guy has to get flipped. So you can rewrite if you'd like, but I have, in this case, I'm going to rewrite in the bottom 2H2SO4 yields 2H2S plus 4 O2s. This is going to give me a delta H that is a positive 470. I had to flip my sign because I flipped it. And then let's see what else we got here. We have the H2S isn't even in the reaction, so it's going to be an intermediate. The oxygen design, it will cancel out as well. I expect these two things to cancel. The sulfur trioxide is on the right side, and the water's on the correct side. At this point, you would note that if I flip this one, I'm just going to write this one below here. I have H2S, and that will cancel with this guy, plus the 2 O2s yields, of course, my oxygens will cancel, and then yields SO3 and my H2O. Again, these are all on the right sides. So I didn't do anything to this thing, so I'm going to keep my delta H at a negative 207. And then finally, I just have a little conversion of a liquid to a gas for the water, and of course I have liquid water here, and I need to make sure that they want it as a gas. So I want to cancel my liquids and go to a gas, so I'll leave it as is. H2O liquid goes to H2O gas, and this will cancel this guy from liquid over to a gas. And I have, so now everything's on the right sides. The last thing I would do is delta H is a positive 484, is make sure my quantities are correct. Everything cancels evenly, and I'll get my overall balanced equation in the end. Notice here that I have two H2S's, and I only need one. So that's an issue. Also notice that when I try and cancel these guys, I'm getting twice as many here as here. So again, I need half as many. Same thing with the oxygen. So it's apparent that, for this thing to really cancel out nicely, I need to cut this top one in half. Down to a 1, down to a 1, and down to a 2. And this is going to cut this down to a positive 235. Okay. At this point in my mind, I'm fairly satisfied that this reaction is going to add to the overall. If you need to have it written out, you can. You go 2H2SO4. Oh, well, we did one of those guys. Plus, I have, so that guy. This guy is going to cancel with this one. So you can write it down if you want. The two O2s will cancel with the two O2s. And that's the, well, I do have the H2O liquid here. We'll cancel the H2O liquid here. So that's only written in half, which is all I want. Product-wise, I have my SO3, and I have my H2O gas. And is that what I want? And yes, that is the reaction that I would like. All right, so at this point, all my reactions now add up nicely. I simply need to take my positive 235, my negative 207, my positive 44, add them up, and I get I have a positive 72 kilojoules, and that would be my delta H for this particular reaction. It's an endothermic process. For every 1 mole of this, I get 1 mole of this. I need to add in some 72 kilojoules of energy, heat. And that is Hess's law. Obviously, it takes a little practice to do some of these things. Only little manipulation they might make on this is they could potentially, given, well, basically we have 3 numbers here. We have our individual delta H's, and we have our addition for the total overall. They could give you your overall and ask you to solve for one of the individual pieces. So they could neglect to give you this one, and you'd have to then subtract off from the overall, do a little algebra, and solve for the individual, which is just the same process, just a little bit different. Thank you very much.